Okay, we are recording. We are continuing our discussion of section 8.6, representation of functions as power series. And we are looking now at, well, we looked at 3 examples. And one of the examples, we actually had to differentiate a power series to help us get the result we needed. So we could write the original function as a power series. Here, we want to talk about integrating integrating a power series. So, no, in this problem, this is example 6 from your section 8.6 ebook here, in the ebook. Find a power series representation for the natural log of 1 plus x. Okay, so we, of course, recognize that the derivative of so like, how are we going to express the natural log of 1 plus x as a power series? Well, first let's take the derivative of the log of 1 plus x. Okay, the derivative of the log of 1 plus x is, the derivative of the natural log of 1 plus x is equal to 1 divided by 1 plus x. And you can express that as the power series that you see in the highlighted box. Okay, because you write 1 plus x in the denominator is 1 minus a negative x. So your common ratio is negative x. And there's the power series. Now, what we can interestingly do is with this equation, we can integrate both sides. We can integrate both sides of that equation above. It's really quite fascinating. Maybe what I'll do is maybe I'll just kind of do it like this. Okay, so if you take the equation above, like you got the yellow highlighted box there, and there's an equation above there where you have 1 over 1 plus x equals that power series. If we integrate both sides of that equation, well, the antiderivative of 1 over 1 plus x is the natural log of 1 plus x. And then that would be the integral of the power series. And the integral of the power series is equal to the sum of the integrals of each term of the power series, right? And so what happens is the natural log of 1 plus x can be represented then as that power series, that alternating power series. Or, well, it's an alternating series, but it's a power series too. And it turns out that if the constant of integration, so that constancy of integration is really the sum of all the little constants of integration from every little integral. And that constant c can be determined to be equal to 0, because if we let x equal 0, the log of 1 would equal 0, and that means that it turns out that the constant would equal 0. So let me just see here. Right, and so it's effectively now you've verified this power series for the natural log of 1 plus x. And you can use this power series to help you with certain problems in section 8.6. This is a result that we've established, and we can use it. Okay, we can use it. Now, there's another result too having to deal with the arctangent. In example 7, they want you to find, in example 7, a power series for the arctangent of x. And they actually show in the problem, in the book, they go through a derivation here. And actually in your homework, you'll go through this derivation. It's one of the beginning examples in your section 8.6 homework. But the arctangent of x can be written as that power series. And incidentally, the interval of convergence for that power series can be shown to be from -1 to 1. But we won't worry about that. this is another result that we can use in problems. Okay, so we have a power series for the arctangent of x, and x, by the way, would be in radian mode. And we have a power series for the natural log of 1 plus x. So let's go ahead and look at an example, yet another example here, where these power series will be useful. Let's take a look at this example. Let me give you a moment to copy the example down. So we want to express this indefinite integral as a power series. Okay, and let me see what, okay. So, you know, if we had, for instance, if we had the, always change that font, always got to change that font. That's funny. So, you know, if we had the integral of x squared dx, we'd say, okay, that's x cubed over 3 plus a constant. And we wouldn't need a power series. But here we have the antiderivative of x minus arctangent of x over x cubed. Do you know offhand the antiderivative of that? Does an explicit antiderivative even exist? Probably not, right? But yet we want to be able to work with an antiderivative for this particular integrand. What are we going to do? Just give up? No. We're going to express that integrand, the x minus the arctangent of x over x cubed, we're going to express that as a power series, and then we're going to integrate the power series. So let's go ahead here to the solution. This is what I want to have here. So first of all, we acknowledge that we have this result. The arctangent of x equals the sum, the series, where we have -1 to the nth power times x to the 2n plus first power divided by 2n plus 1. Okay. And here's our integral. So what we're going to do here is we're going to replace this arctangent of x with its power series. And in this case, it'll be easiest to put in for the arctangent of x the actual power series written out in this form. Okay, written out in that form. Okay, are we okay with everything so far? The terms, of course, the terms of the power series, you know, like just for an example, this second term, negative x cubed over 3. How are they getting that? Well, okay, that's the second term. That's when n is 1. So that's -1 to the first power times x to the 2 times 1 plus 1 power, all divided by 2 times 1 plus 1. That equals negative x cubed over 3. Okay, so All right, so we'll replace the arctangent of x here with its power series. And that's what we do. We do that right here. And it turns out that some nice things are going to happen. Turns out some nice things are going to happen here. The x terms simplify out, right? Those two x terms simplify out. And then the negative gets distributed through all the terms. And so this gives us then this integral here. Are there any questions up to this stage here, up to that step? All right, well, now what we're going to do is we're going to divide the x cubed in each of the terms in the numerator. Okay, so like how do we get 1/3? How do we get the 1/3? Well, all right, if we take x cubed over 3 and divide that by x cubed, just like x cubed over 1, that's going to give us x cubed over 3 times 1 over x cubed, and that equals 1/3. So that makes sense. And let's see. Let's see here. Let me do maybe another term just so that this is very concrete. Take these checks off here. Okay, let's say you had negative x to the 5th. You know, you have negative x to the 5th. Negative x to the 5th over 5 divided by x cubed. Right? So, you know, I'm focusing now on this guy here. That equals negative x to the 5th over 5 times 1 over x cubed. And that will give you a negative x squared over 5, which is the second term here. It's a negative, right? So I'm just trying to show you how we're getting these terms. Are there any questions on that? Make nice boxes here for the recording. There we go. Okay, so all right, we have the integral of a power series. At this stage here, we have the integral of a power series. And it would be nice now to find out what the formula is for this particular power series, right? I need, you know, what's the formula? What's the formula for that particular power series? Well, let's see if we can figure it out. I'm going to go to the whiteboard. Let's go to the whiteboard. Okay, so this is a little like with sequences. When you were working with sequences, you have to figure out the pattern, and that's what we're going to do here. So Let me see here. We have our series 1/3 minus x squared over 5 plus x to the 4th over 7, and so forth. So the first term, well, we know we're going to need a -1 to the nth power because this is this series alternates. Okay, and so this could be like -1 to the 0th power. That would give you a positive. Okay, and then well, and so let me see here. Let me just go -1 to the first power, -1 to the second power. You know, that's clinching the negatives and positives. Now on the denominator, we have 3, 5, and 7 in those denominators. Well, so if we had 2 times 0 plus 3, that would give us a 3 in the denominator of the first term. For the second term, if we had 2 plus 1, 2 times 1 plus 3, that would give us a 5 in the denominator. That's good. And then for the third term, if we had 2 times 2 plus 3, that would give us a 7. So far, so good. Now, we have to worry about our x values. Okay, so it looks here like all the powers are even. The 1/3, we could think of that as 1/3 times x to the 0th power. Even powers we're going to get by raising, well, so the 0th power is 2 times 0. The second power is 2 times 1. The 4th power is 2 times 2. I mean, this is like the pattern. So this particular power series would be equal, the formula would be the summation where n equals 0 to infinity of -1 to the nth power times x to the 2nth power, all divided by 2n plus 3. That's the power series. That's the formula for our power series. So sometimes it takes a little time to sort of figure it out, but you know, again, you can figure it out. You can figure it out. Are there any questions on that? Okay. How many, is it helpful to kind of enumerate the terms like I've done here to kind of write them out and to I mean, I could have just said, hey, this is the power series formula. Is it helpful taking a little time to do what I did there? Okay, thank you. All right, Tosh is very helpful. Jan, Mario, wonderful, wonderful. I like to survey students to get their thoughts. All right, well, great. Well, let's get now back to the problem. Let's get back to the problem. Okay, so this is where we are. And now we want to integrate the power series. Okay, we want to integrate the power series, right? This power series, and we substitute in the formula for that power series. And we have the integral of a sum. At this point, we have the integral of a sum. Well, remember, if you have the integral of f plus g, that equals the integral of f plus the integral of g. So the integral of a sum is the sum of the integrals. that means that I can take my integral of my sum here, separate this a little bit, and write it as the sum of the integrals of each term, which I have here. Absolutely beautiful mathematics. Absolutely beautiful. But what we have here, right, is we have here, we're integrating with respect to x. And how can we treat the -1 to the nth power and the 2n plus 3? What are those treated as with respect to this integral? Constants, that's right, Tosh. Because -1 to the nth power and 2n plus 3 do not depend on x. So that means we can factor out -1 to the nth power over 2n plus 3. We can factor that out from the integral. And the antiderivative then here of x to the 2n power is just x to the 2n plus 1 power over 2n plus 1. And then we have this constant of integration, big constant of integrations, which is really the, for every integral, every indefinite integral, you have a little constant of integration. But if you add them all up, you'll get this big constant of integration. And so now you have a power series for your integral. In other words, what we can say is that this here is equal to the antiderivative of, hold on, it's the antiderivative of x minus the arctangent of x over x cubed. Okay, we can say that. Are there any questions on that? All right, so absolutely amazing, absolutely amazing. And the thing is, you see, again, this kind of problem, maybe this kind of problem in your web assigned homework, the answer, you'd have a multiple choice. And maybe this particular answer here that we got, maybe that's not one of the choices. So again, you need the ability to rewrite the summation. So maybe they have, like, as part of the answers, summations that start at n equals 1. Well, can we rewrite this power series? The answer is yes. Let me show you that. So here's the formula that we found, and it starts at index n equals 0. That summation. Now, if I want to start at the index n equals 1, that now I'm changing the index to a higher number, n equals 1. If I do that, then I have to adjust all the n values by subtracting 1. You see? That's the adjustment I have to make. Maybe I'll put arrows. So everywhere I saw an n value, up here. I replace it with an n-1 value. Because, like, for instance, the first term, the first term, let me just, this is in the recording, but let me just, so the first term is the first term of this series going to be positive or negative? The first term of this series. Is it going to be a positive term or a negative term? Of course, -1 to the nth power determines that, and you start at n equals 0, so right answer. First term is going to be positive. Well, if I start at n equals 1, then -1 to the n-1st power is the first term of the series positive or negative? Positive. It would be positive. That's right, Ann. So you have to have it so that this series here equals the second series. And so you had to make, if you adjust the index, then you have to adjust everywhere you see an n in the series formula. And if we simplify things a little bit, this is the final, this is the formula. And this might be what you see in WebAssign. So don't try to, like, if you have an answer and you feel pretty comfortable with it, and you're not seeing the same answer in the WebAssign choices, go and try to adjust your answer. Maybe like for instance, your answer has starting index n equals 0, and there's some answers in WebAssign that have index starting at n equals 1. Well, if the choices where n equals 0, that index don't work, you could try the other choices and rewrite your power series. Don't answer too quickly, okay? So that is now using integration to help us find a power series. How many think this is like really, really cool stuff, what you're learning here? All right, Taj is liking it. This is probably the best stuff you've learned all day, right? All right, Angie's liking it. You learn good things in your classes, but hopefully this is one of the best things you've learned today. Are there any questions? All right. All right. Well, so I want to mention one more thing here. In example 8 in the textbook, let me go to example 8 if you're good here. So here's a problem in example 8, which you'll need to look at. It'll be helpful for you for the last couple problems in the homework. Well, yeah, for sure. They want you to evaluate an integral as a power series, but then they want you to approximate the definite integral correct to within 10 to the -7th power. So for this problem, the steps are pretty straightforward. Okay, you rewrite the, well, hold on, let me just try to, you find a power series for your integrand, 1 over 1 plus x to the 7th. And then what you do is you get a power series for the integral of your, the integral, right? So, I mean, we looked at a problem. The problem we just did, the same kind of steps are involved. So I think this will be pretty straightforward. But then you have to compute, you have to approximate the integral correct to within 10 to the negative 7th power. And what we have to recognize is this is an alternating series. So with an alternating series, you can use the alternating series estimation theorem. Okay, and so they mention that. Okay, here what they do is they write out the definite integral, where they put in the values 0 and 0.5. Well, when you put in 0 for x, you get nothing. But when you put in the half, the 0.5 for x, you get that series. And the alternating series estimation theorem would be used since you have an alternating series. You'd use the alternating series estimation theorem to get you an estimate within the accuracy you want. And that being said, in the problem, they finally come up with saying that you would need the first 4 terms of the series. Okay, so that's an example that will be helpful for you to look at for the last couple problems in your section 8.6 homework. Are there any questions on that before I stop the recording? This was example 8 from section 8.6. Okay, let me stop the recording.